Thursday is going to be our final. So exactly a week from today at 2 p.m. We're going to be in this room. We're going to be doing our final exam. It's going to be from 2 to 4. Right? So you will have a full 2 hours to do the exam. It is going to be a cumulative exam that's going to cover everything from what we started from the beginning of the semester till the end of the semester. However, I did say that the bulk of it, about 50% of it, is going to be the later chapters. So in our review, I'm going to start off with those later chapters, 12, 13, and 14, 15, and then we'll go and review the previous material as well. Because I do want to emphasize those few chapters before we get to anything else. So please make sure you guys are here on time. You have your Scantron, you have your calculators, and you have your cheat sheet. This time the cheat sheet, it is still going to be one page but double-sided. So please make sure you have that. Prepare a good cheat sheet. That's a very important part of the exam for you to prepare, and hopefully you guys will do well. Any questions on the final exam?
Only one sheet?
So double-sided. Okay. Yeah, double-sided. So you can have two sides with one page, yes. Okay, so chapter 12, let's quickly go over this again. Acids and bases. We went over the definitions of an acid and a base. So make sure you have that on your cheat sheets. We have two different definitions that we had. We called it Arrhenius, acid and base, and then the Bronsted and Lowry. I'm not really going to ask you guys definitions, right? They're not added to us right now. But the idea is you should be able to identify an acid and be able to identify a base. So keep that in mind. An acid is something that produces hydrogen, or in other words, is a proton donor, right? It donates a hydrogen, and a base is something that is going to accept hydrogen. Or in other words, it can also be a OH generator, right? So when you add it into water, it produces OH minus. Now that we know about equilibrium, you have something called strong acids and weak acids. A strong acid is something that will almost go to completion, right? It's a reaction that goes all the way. A weak acid is something that is under equilibrium. It does not completely dissociate. Some of it dissociates and some of it doesn't. It is a partial ionization. You should be able to identify those if you're given a specific reaction. Then you should be able to find out what is the acid, what is the base, and also what is the conjugate acid and what is the conjugate base. The acid becomes the conjugate base, right, after it loses a hydrogen, and the base becomes a conjugate acid when it receives the H+. Okay, here's an example. So if you want to have one example of that on a cheat sheet, that's perfectly fine, or anything to help you identify which one is which. Acid-base reactions, if you're asked to write down the reaction, you guys should know, if you add an acid to a base, it will always produce water as one of the products, and then the remaining two elements are going to be the salt. So the hydrogen from the acid and the OH from the base are going to combine to give you water, and you're going to be left with your salt. So by now, some questions in the exam, quite a few of them will be, these are your reactants, you have to predict what the products are going to be. So if you see that you have an acid and a base, you should always write down water and then figure out what the salt is going to be. Right here you have your breakdown of your molecular equation, your ionic equations. Your net ionic equation for an acid base is always going to be exactly the same. H plus OH minus gives you H2O. Then one of the other important parts of this chapter, right, is going to be your calculations for pH. Make sure you have your equations. You should have these four equations written on your cheat sheet, please. Right? These are the four equations you will likely have to use. So make sure you have all four of them written down. You probably won't need to use all of them, right? But definitely you need to use at least three of them, right? pH to POH and POH to pH. And I would like to add on to that the inverse, which people tend to forget. Right? What happens is if you have hydrogen, it's easy to calculate pH, but people tend to forget how to do the opposite. For the opposite, it is the concentration of H equals 10 to the power of negative pH. Same thing for this one. To calculate concentration of OH minus, it is 10 to the negative POH. Okay, so the inverse of the log is 10 to the power of. Okay, so these 4 equations, or now 6 equations, are going to be crucial for anything to do with chapter 12. So you can definitely expect a few calculations based on that in your exam. Okay, there are some practice calculations. Right, for measuring acid and base concentrations, we use the litmus test. We have a few different ways of measuring. Then we have our acid-base titrations, which we have done in the lab by now, right? We've done 2 acid-base titrations, so you have an idea about how to do the calculations. So this is one of the stoichiometric calculations you will get in the exam. Okay, so it's an acid-base calculation. You are adding a base usually into our acid, and you will have to do your calculations. This is the equation that I would prefer you guys remember. MAVA divided by CA equals MBVB divided by CB. Now C is the coefficient of the balanced chemical reaction. This equation is valid for all cases. In some cases, the previous one, if it's not a 1-to-1 ratio, you cannot use that. But this one is always valid. So this is what I would prefer you guys use and have written down in your cheat sheets. Okay, so molarity times volume of the acid divided by the coefficient of the acid equals molarity and volume times the base divided by the coefficient of the base. Now keep in mind, molarity is always given to you in moles per liter, and the volume has to be in liters. Except in this case, it just has to be consistent. Right? You could have it in milliliter, that's perfectly fine. They'll eventually cancel out. But just to be safe, it's always a good habit to convert every volume to liters, just to avoid any errors. Right, we have some practice over here, practice calculations, so make sure you guys go over that. Now for buffers, as I said, I'm not going to ask you guys about buffers, so we don't really need to know too much about buffers. It's just something for your own reference for later courses to know what a buffer is. For example, our blood is a good buffer, and there are other types of buffer solutions. Right, we're not going to be preparing buffer solutions and stuff. Okay, so we have 4 chapters 12. Any questions? Okay, let's go ahead and move on. Chapter 13. Right, this is also a chapter that we went over pretty quick. Right, we didn't go over the whole entire chapter. A lot of it was skipped over. Right, we talked about kinetics, right, reaction rates, and there are 3 factors that are going to change the reaction speed, your reaction rate. First is the concentration, second is the temperature, and third are some energy changes. Right, for example, the catalyst that we talked about. First one, we said an increase in concentration is going to increase the reaction rate. Right, make sure you know the order in which things happen, which makes sense. Second, also an increase in temperature is also going to increase the reaction rate. So it's a direct relationship between temperature, concentration, and reaction rate. Everything goes up at the same time, or everything goes down at the same time. Then for your reactions, right, for energy changes, we have to know if it's an exothermic or an endothermic reaction. And then we wrote down our energy diagram, right, where something goes from one state to another state. It goes from the reactants to the products. Based on the shape of the curve, you should be able to predict if the reaction is endothermic or exothermic. In this case, you're starting off at a higher energy and you're going down to a lower energy. Therefore, it is negative, and a negative tells you that it is exothermic. Right? If the final products are lower than the starting reactants, then it's going to be exothermic. If the opposite is true, it will be endothermic. Then we have this little thing over here that we call the activation energy. That's the energy needed for you to start that reaction and get it going. Okay, so not all reactions can start simultaneously. They will sometimes need a bit of an activation energy. So in this case, this was an endothermic reaction, right? And then we said there's something called the catalyst, which will bring down the requirement and bring down that activation energy, but it plays no role in the actual energy of the reaction. So reactants are in the same place, products are in the same place. It just makes it easier for that reaction to happen, therefore speeding up the reaction. Okay, so it is just going to reduce the activation energy. Now over here we have an example of an endothermic reaction. And as the example says, in terms of the energies, you should be able to predict and even calculate what is the total energy loss and what is the activation energy from this type of diagram. Okay, so if you just measure the difference between A and B, that will be your net energy change. And the difference between your reactants and the top of the peak is going to be your activation energy. Now in this case, it's an endothermic reaction, so the activation energy is really high. Whereas in this case, earlier, the activation energy is a bit smaller because your reactants are already starting off pretty high in the energy diagram. Then we talked about equilibrium reactions, which are two-way reactions, right? They happen simultaneously at the same time. You have reactants and you have products. Eventually they start reacting and they reach what is called an equilibrium, where the concentrations do not change, but the reaction is still occurring. Okay? But the forward reaction is equal to the backward reaction. Right? So there's no effective reaction. It doesn't seem like there's a reaction going on, but there is still some reaction going on both sides. Okay, so it would be good to have a diagram like this in your cheat sheets, right? That gives you a scenario and you can say that this is your activation energies or whatever you have over here. In this case, it is an endothermic reaction. So make sure you guys have examples of both if you want and able to identify what determines if something is endothermic or exothermic and how you can calculate the activation energies. Okay, we have a few examples here as well. And the last thing that we had in this chapter was Le Chatelier's principle. This is a very, very important principle when it comes to equilibrium reactions. It means that you can change the equilibrium position. You can shift things towards the product, or you can shift it towards the reactants, depending on what you want. This allows us to play around with where the equilibrium stands. Now the idea is, what happens is it's similar to this kind of two tanks that are connected with water, and they both have nozzles. What happens if you add any reactants, it's going to push the reaction to the right. If you remove reactants, it's going to bring reactants to the left. So the equilibrium shift in the left direction. So when we're talking about a shift, we're going to say, does it shift to the right or does it shift to the left? Does it shift to the products or does it shift to the reactants? That's what we're trying to figure out. So not only adding or removing, right, on the reactant side, you can add or remove on the product side as well. If I add products, it's going to shift the water to the left side. If I remove the products, it will shift towards that direction. Because what happens is any change is going to try to compensate for the change that you made. If you added more, it's going to go ahead and react. If you removed, it's going to go ahead and try to replace what you have removed. Right? So that's a good way of thinking of it sometimes. Now that is for concentrations. We said that heat also plays a role in our equilibrium. Now, if you have, in this case, an endothermic reaction, right, which means you're adding heat to it, heat is a reactant. If I add heat, it will shift the reaction to the right. That means I'm raising the temperature. It will act like I'm adding heat. I'm adding a reactant, and it will shift it to the right. If I remove the heat, it will shift it to the left. So heat will behave like a reactant or a product depending on the type of reaction. This is an endothermic reaction, right? If it's an exothermic reaction, heat will be on the product side, right? And it will behave the opposite way. Right, and then we got into pressure, and if I'm not mistaken, we skipped over this part, right? I don't think we went into this part in too much detail.
There's questions on the homework about pressure and equilibrium.
Right, but I believe that we skipped over it, right? So I'm not going to ask you guys about it in the exam. Okay? Unless you want me to go over it now. No, that would be unfair for the people who haven't come today. Okay? So we will not be getting questions about pressure, but temperature and concentrations are definitely going to be asked, right? So make sure you guys know how the equilibrium will shift based on what you have added or removed. Okay? Any questions? Chapter 14, we talked about redox reactions, right? So reduction and oxidation, two things that can occur at the same time. Make sure you have the idea of what is a reduction and what is oxidation, the definitions if you need them, right? Have that on your cheat sheets. But the main thing will be to identify which atom is being oxidized and which atom is being reduced. And to do that, we have to figure out what the oxidation states are. Right? So we have to figure out what the oxidation state is, right? And usually you have the oxidation states of certain atoms, but other atoms you will have to calculate what the oxidation state is. If you have an element, a pure element in its elemental form, that means it's not reactive with anything else. So it's Na, it's O2, it's H2, it's PT. All of those are zero oxidation states. Okay, they are zero. Right, and monoatomic ion is going to have the oxidation state of its ion, right, of its charge. And then the polyatomic ions, it actually depends, right? So you should be able to calculate the different oxidation states of all the different atoms in the reaction. Then once you know which one is changing, you can identify which one is being oxidized and which one is being reduced. If you see an increase in charge, for example, sodium went from 0 to +1, we call that oxidation. If you see a decrease in charge, in this case, you saw the hydrogen went from +1 to 0, that is what we call a reduction. Oxidation is an increase in charge, a reduction is a reduction in charge. Okay, that's the way I like looking at it. But other people, in terms of actual definition, it is related to the number of electrons. So oxidation is a loss of electrons, whereas reduction is a gain of electrons. We went over a few different types of redox reactions. Right, so once again, this helps you predict what the products are going to be based on reactants. Right, in this case, you have just simple oxidation, or you have a metal reacting with a non-metal. The metal will always be oxidized and the non-metal will always get reduced. Then you have combustion reactions where you're reacting something with oxygen. It will usually, oxygen is an oxidizing agent, so it will get reduced, and whatever oxygen reacts with will get oxidized. Okay, and here we have a few examples. Right, in this case, the carbon is getting oxidized and the oxygen is getting reduced. The oxygen will go from 0 to -2, and in this case, the carbon went from -1 to +4. Now, metal displacement reactions. Now keep in mind this is a single displacement reaction where you have one metal taking the place of another metal, right? The metal that changes from 0 to +2 in this case is the zinc, and that is being oxidized, and the copper is going from +2 to 0, and therefore it is being reduced. You will usually be given an equation like this, the molecular equation, and asked to find out which one is being oxidized, which one is being reduced. So over here the zinc is a 0 charge, and the copper is a +2, right? Because we know sulfate is -1. And then from there we know zinc is -2, so it went from 0 to +2. Therefore it is oxidized. Okay, so this is just another way for you to identify what is being oxidized and what is being reduced. Activity series is not included, right? So you will not be asked anything about the activity series, but this is a way for you to know which one is going to react in what direction, which one is more reactive in terms of the metals compared to others. So I will not be asking you about the activity series. Okay, and that's all we have for chapter 13. Sorry, chapter 14 even. Okay, any questions? All right, the final chapter, we just did it a couple days ago, so I don't think we need too much of a review for these. We talked about organic compounds, right? You will have to know what is an isomer and be able to predict the different types of isomers that a product or a reaction can have. Not a reaction, I mean the formula. So I'll be giving you a formula like I did over here, and I'll ask you to draw the different types of isomers, right? So you'll have to figure out what kind of isomers you can draw from there. For example, over here you have 2 different isomers. Over here you have 3 different isomers. Okay, so you have a variety of different isomers that you could draw. Then we have our Lewis structure going to the condensed structure, so you should be able to go between the two. Right? And then you should also be able to read and identify a skeletal structure. I can give you a structure like this and ask you for the chemical formula. Right? How many carbons does it have? Right? So you should be able to count how many carbons are present in this type of skeletal structure. Okay? Keep in mind, every single curve, every single vertex, as they call it, or endpoint, is a carbon. So for example, you have 1, 2, 3, 4, 5, 6 over here, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 carbons. Yes?
Will these be carbon?
Yes. If it is anything other than carbon, it will be shown. Right? So for example, if it's an oxygen, it has to be written oxygen. If it's, for example, nitrogen, it has to be written as N. If nothing's written, then it's always going to be carbon. Okay? That's a rule for organic chemistry for the skeletal structures. Okay? So those are the different ways organic structures are drawn. Then for your cheat sheet, make sure you have all of these names written down. Right? So identify what is the base structure. Based on how many carbons you have, you should be able to tell me the base name. Meth, eth, pro, but, pent, hex, hept, oct, non, and dec. Right? So usually you should be able to identify which one it is. And then after you know which carbon it is, based on the first part of the word, you know how many carbons there are, you should be able to figure out how many hydrogens there are from the reaction, from the formula that we have over here. If it is an alkane, Cn equals H2n plus 2. So if I have 5, the number of hydrogen, it will be 2 times 5 plus 2, so it will be 12. Okay, so make sure you know how to use that equation for an alkane. And that equation stands true regardless of what type of isomer you have. If it's a straight isomer or a chained isomer or a branched isomer, they will all be exactly the same. Unless you combine them in a circle And now you have your cyclohexane or cycloalkanes. So for a cycloalkane, you're going to connect them in a cycle. And when it comes to the number of hydrogens, there are 2 less because now they're connected in a circle. And for the reaction, for the equation, the number of hydrogens is equal to CnH2n, right? So double the number of carbons. Then other than alkane, we have alkenes. Alkene means you have a double bond. And then alkyne means you have a triple bond. Okay, so if you're given a structure, I'll tell you right now, these last questions, you'll be given a structure and told to identify what are the different functional groups. An alkene is a functional group, an alkyne is a functional group. Right? That means you can find out where it is on your diagram. Right? So alkene is a double bond, alkyne is a triple bond. Then you have your aromatic ring, which is a cyclic structure which has alternating double bonds. Right? We call that a aromatic ring. Right? So those are our 4 types of hydrocarbons. And then we went over our 6 functional groups, and that was the last thing that we had. Make sure you can identify each one and know which one it is. Have all 6 of these written down on your cheat sheets. Right? An alcohol is something that has OH connected directly to a carbon. The carbon can be connected to anything else that is another carbon or a hydrogen. Okay? Yes?
Are there aromatic rings for triple bonds?
Huh. Probably. But it will just be a single bond. There will be one double bond. So for example, same thing with the 5. So if you have a 5-member aromatic ring, there are 2 double bonds that keep switching around. Right? So I'm assuming it might not be very stable, but you could have a 3-member ring, but it can only have 1 double bond. Right? So it'll be similar to the 5-member ring or 7-member ring. It cannot have the same carbon having 2 double bonds. Okay, because that makes it very unstable in terms of its structure. But even this one, it will actually be very unstable. Right? When you get into later studies, you'll study something called steric hindrance, which doesn't allow them to get too close to each other. Right? If you have 3 of them connected, then you're forcing the bond to become 120, which puts a lot of stress on the molecule. Right? Whereas it prefers to be further away from each other. So probably possible, but unlikely. Right? But even the 4-member ring is not very likely. It is possible, but 5 is this is very stable, and this is also very stable. Right? The 5, 6, and above. Okay. Any questions? Okay. Once again, back to our functional groups. An alcohol is going to be a carbon connected to OH. If I remove that H and connect another carbon to it, that is what we're going to call an ether.
There.
Okay, so if you have an oxygen in the middle, connected to 2 carbons, and they're connected to other carbons or hydrogens, then that is an ether. An aldehyde is when you have a carbon connected to a C with a double bond O and a H. Right, this is what we call an aldehyde. Right, that C double bond O makes things a bit different. We call that your carbonyl group, which we went over here. If I take out that hydrogen and connect it to another carbon or carbon connected to other stuff, we call that a ketone. Right? So these are part of the same family. An aldehyde and ketone is the same family. Alcohol and ether are same family. Third one is carboxylic acid, where you have, once again, the C double bond O, but you have another oxygen. And if I remove the hydrogen connected to the oxygen and make it into a carbon, that is going to be an ester. Now, one thing I do want to note, try not to get confused between an alcohol and a carboxylic acid. They both have OH groups connected to a carbon, right? As you can see, this is the OH connected to carbon. Over here, you also have an OH connected to carbon. But if that carbon has an oxygen on it, then that's a carboxylic acid. An alcohol, this carbon is only connected to other carbons or hydrogens. Okay, not a C double bond though. Does that make sense? So you should be able to identify all the different oxygen-containing functional groups. Later on, you'll get into nitrogen-containing functional groups as well, which we did not go over. But you'll be given a structure and told to identify all the different functional groups that are present in that specific structure. So please make sure you know how they look and you can identify all of them in a structure. Any questions? Good for the last few chapters? Okay. Now let's look at what we did at the beginning of the year. It's been a while. All right, at the beginning of the semester, we started off our first class with measurements, right? Chapter 2. The main thing I actually want you guys to know from this chapter right now has become irrelevant for us. Right? By now, you should know how to go from scientific notation to regular calculations, or regular standard numbers. But the only thing I would probably ask you guys from this chapter specifically or directly would be your conversions. Right? So please make sure you are very comfortable doing unit conversions. This is going to be the priority for chapter 2. Right? I still ask you direct questions. I give you the equation, or I give you a certain number, and I give you the conversion rate, and I ask you to convert it to something else. So that will be the most important part for this chapter. And keep in mind, this rule is important for all the chapters. Right? Any calculation question you can have will possibly have a conversion involved. Alright, so make sure you're comfortable with doing your dimensional analysis, regardless of how many units you have. Right, keep in mind, sometimes you have the cubes. Right, so make sure you practice on how to do the unit conversions over there. Right, and then also keep in mind, you should have your equation for density as well. Yes?
We be given conversion that we need or no?
You'll be given the basic conversions that you need, yes.
Alright.
Now, the only conversions I will not provide to you are the conversions of time, right? But distance and stuff like that will be provided for you. But time, as in 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, you guys should know that. That's not going to be provided. Okay? Now, density equals mass over volume. I went over a few different ideas about density and conversions for your temperatures. Right? Please make sure you guys know how to do the conversion for your temperatures. Once again, this is an equation. This will not be provided to you. You are expected to know this as well. Okay, so these are the equations, right? To go from Fahrenheit to Celsius. If you have Celsius, you're going to use this equation here. Fahrenheit equals 9/5 times C plus 32. Or instead of the 9/5, as I said, I prefer using the 1.8. That's just what I'm used to. Right, and then if you have the Fahrenheit, you're going to subtract 32 and then multiply by 509 or divide it by 1.8. So make sure you have those equations and you can comfortably convert between Fahrenheit and Celsius. And then from Celsius, you should be able to convert to Kelvin. As we did in our last exam, I think a lot of people messed up on that question, where you guys forgot to convert it from Celsius to Kelvin when doing your gas equations. So please make sure you know, if you have Celsius, you're going to add 273.15 to get you to Kelvin, right, which is our absolute temperature. All measurements in chemistry are always done through Kelvin. Right, and that's all we had for chapter 2. Chapter 3, we started getting into the definition of an atom. This old stuff by now. This is very easy for us, right? Right, figured out what the periodic table was. We have a law of conservation of mass. went over the periodic table and we're able to identify what part of it is metals, what are non-metals, right? Those are the important part. Right, we have your groups, you have your periods, right? The metals are everything that we have on the left side, bottom left side of the equation of the staircase that we have over here, right? Which I wrote over here. So I will just ask you guys what is a metal and non-metal. So anything under this staircase is going to be a metal, and everything above to the right of it is a non-metal. Okay, so I'm not going to ask you too much about metalloids. Okay, so we have our non-metals, our metals. Right, we define certain types of metals, right? The first group is alkali metals. Yes, question? Now, just for consistency, right, you do have a cheat sheet with the periodic table. You guys will have to use the one that I provided for the example, right? But if there's anything you want to do on your cheat sheet and draw certain things on the periodic table, that you can do, but nothing other than that. So group 1A, so these are your alkali metals. Group 2, we call them your alkaline earth metals. Group 7, which are at the end, we call them the halogens. And group 8, we call them noble gases. These are the specific groups that we have given names to. Okay, other than that, they don't have their own specific name. They're actually just named off of the first element on the top. Then we talked about the particle. We have the nucleus in the center, right, which has all the positive charge, and we have the negative electrons roaming all around it. Now the particles are the proton, neutron, electron. Protons and neutrons have a mass of 1 atomic mass unit, 1 U, and electrons are considered negligible in their mass. The charge on the proton is +1, right? P is for positive, right? So the proton is positive, neutron is neutral, and the electron is negative. Now the identity of the atom depends on the number of protons only. Okay, and then you have two numbers in the periodic table, right? You have your atomic number and you have your mass number. The larger one is going to be your mass number. Then you have isotopes, right? Different atoms which are the same identity, but they have a different number of neutrons. They all behave exactly the same, regardless of how many neutrons they have. But then because of that, you have what is known as an average atomic mass. So most of our atomic masses are in decimal form because it is the average of all the different isotopes that are naturally occurring. Right? And it is what is known as a weighted average. So make sure you guys practice on how to calculate the average, the weighted average molecular mass. Now when it comes to electrons, if you lose or gain an electron, we call them ions. Right? You have your positive ions or negative ions. And then over here, we did a bit of an example. Right? So please expect something like this in the example, right? As we had done in the quiz as well. You might be given some of these values, or right, you will only be given this, and from this you should be able to predict how many protons, how many neutrons, and how many electrons. Yes?
Will we be given an electronegativity chart?
Yes.
Okay.
You will definitely be provided electronegativity for things you will need, or just the whole chart. Yes.
Thank you.
Any questions? You good? I'm trying to cram the whole semester into one day. It can get a bit tough.
I think we got it.
Alright, chapter 4, we started talking about the electromagnetic spectrum. This is the one chapter about light and electronic structure. So, have this breakdown given to you, right? It would be good to have this in your cheat sheet, where you have the lower ones, TV, radio, microwave, infrared, visible, UV, X-ray, and gamma, right? So make sure you understand the order in energy, the order frequency and how that affects the specific part of the electromagnetic spectrum. Your visible spectrum goes from 350 to 700, approximately, in this book. Now we have our wavelength, right, which determines the color of anything that we see. And this is our equation that relates our speed of light, which is a constant, right? It's exactly the same, always the same, 3 times 10 to the power of 8. And it relates that to our wavelength and our frequency. Now, since our speed of light is the same, wavelength and frequency have to balance each other out. If one goes up, the other has to come down. We call that an inverse relationship. Okay, here's an example of using that equation. Now here you have 2 examples of waves. As you can see, the one on top, it has a longer wavelength, therefore it has a lower frequency and it has lower energy. Whereas if you have a short wavelength, you have a high frequency, and that means high energy. So make sure you understand the relationship between the 3 factors that we have and what directions they go in. Okay, then we talked about different color, the line spectra. Right, these are examples of line spectra, Bohr model. Right, you have your hydrogen atom, you have the different transitions, and then you have your quantum chemistry. Right, so we have our different levels. We have our 1, 2, 3, 4, and then within that we have our sub-levels S, P, D, F. You guys remember this stuff? Right, and then within that you have different number of orbitals. So the idea is, if you are given a specific molecule with a certain number of electrons, you should be able to fill up the orbitals and tell me what is the electron structure. Same thing. There we go. Right, so you should be able to say it's 1s2, 2s2, 2p3, 2p5, whatever it will be, right? And then keep going until you reach a specific level. Until you complete all the electrons, right? You have to fill every single electron. Now, if you add all of these numbers on top, it should give you the total number of electrons. And the last electron that you filled will tell you where it is on the periodic table. Okay, so the periodic table is based off of these electron configurations. For example, potassium, the last one is 4s1, so therefore it will be in the 4th column and it will be the first one in the 4th column. So first one is potassium. Whereas argon, the last one that was filled with was level 3, and it has 6 electrons in level 3. So you come down to the 3rd one, and then you go, sorry, not 6, it has 8. 6 plus 2, 8. You go 8 to the right, and it'll be the last one that is in that 2nd level. Okay? Then we have a way of simplifying our electron configuration using our noble gases, because these are complete configurations. So based on where you are on the periodic table, you're just going to go up 1 and to the right, and that's going to be your noble gas. And then from there, you have to start counting how many electrons you have and start filling up your electron configuration. For example, titanium. When I go to my periodic table over here, titanium is right here. Right, so in order to find out the electron configuration, I would go up 1 to the right and write argon. After that, after argon, which is 18, I have to go this way and I have to get to titanium. I'm in the 4th row, and this is, all of these are S, so I have 4s2. And then this one, right, our transition metals, keep in mind, go down by 1 level. So this is now 3d. So I have 3d, 1, 2. So you can see that part over here in the middle is our D block. And it's always one less than the group. And this is your F block, which is two less than the group. But I'm not gonna ask you guys any examples with the F block. Okay? But do expect stuff from the D block. Okay? That's what we have. Our noble gases, electron configurations. Yeah, that was the main thing. This just went over examples on how to do that. Okay, any questions? What was that, chapter 5? No. Chapter 5, we started getting into chemical bonds. 5, 6, 7, right? These are all, everything from here was mostly related to each other. We started talking about the different types of chemical bonds and chemical compounds. We started talking about valence electrons and the octet rule, right? So we started drawing Lewis structures, and keep in mind everything has to follow the octet rule. So hydrogen, right? It only needs 2. Same for helium, right? It only has 2, and it is very stable. Right? You have ions, positive or negative. You have your cations, which are positive. You have your anions, which are negative. These are going to be all of your transition metal cations. Right. Keep this in mind. This table should be there in your cheat sheet. If not as a table form, all of these charges should be there in your cheat sheet. Right. So you know what is the charge on every single one of these atoms. If they have multiple atoms, if they have multiple charges, make sure you remember to put their charge in Roman numerals when you are naming them. Those are for positive and negative, so all of them are in that one chart. Now when it comes to naming, right, the naming of the anions, we're going to remove the last few letters and we're going to put IDE at the end. So chlorine becomes chloride, oxygen becomes oxide, sulfur becomes sulfide, and so forth, so on. Alright, so make sure you remember the namings. When it comes to your polyatomic ions, I have listed the ones that are going to be important and the ones that you will have to have in your cheat sheet. Right, so main ones are going to be nitrate, carbonate, phosphate, hydroxide, sulfate, and chlorate. Right, most of the ones with ATE. These are the most common polyatomic ions that are used. Okay, as well as ammonium. Don't forget that. That's the only positively charged polyatomic ion that we have. Okay, when it comes to the naming, right, then we got into the ionic bonds. This page summarizes all the polyatomic ions and the charges. Now, then we have the ionic bonds, which is a bond between a positively charged ion and a negatively charged ion. Now, they're usually in this ionic lattice where you have a positive, negative, positive, negative, positive, negative arrangement. Okay? Now, based on the charge, you should be able to predict what the formula is going to be. Keep in mind, the formula only depends on the charge. You have to try to make the charge 0. Right? So if I have a K plus and S2 minus, in order for me to have a total of 0 charge, I need 2 potassiums and 1 sulfur. K2S. Now the shortcut that we talked about is going to be our swap, right? Where you take the charge on the positively charged ion and it becomes the subscript of the negative, and you take the charge on the negative and it becomes the subscript of the positive. So the 2 over here comes down here, and the 3 over here comes down here. If you have more than one polyatomic ion, it has to be in brackets. Okay? Now the only rule, if you are going to be using the swap, if both of them are an even number, for example, if you have 2, 2 or 4, 4, you're going to divide it by 2. Or even 3, 3, you're going to divide it by 3. You have to have the simplest ratio. Naming, the metal ion is just the name of the metal ion, and the anion is the name of the anion with IDE at the end. If it is a single non-metal, if it's a polyatomic ion, it is the name of the polyatomic ion. Anything which has more than one charge, don't forget to put the Roman numerals so I tell you what the charge actually is. Right? We practice quite a bit in detail when it comes to naming. Then we went into covalent bond. Over here in covalent bonds, now we know that we are sharing electrons and not transferring them completely. Right? So from the Lewis structure, you can know which ones are your lone pairs and which one are the bonding pairs in your Lewis structure. And when it comes to naming covalent compounds, you have to know these prefixes. These prefixes go on both the nonmetals, right? The first one and the second one, unless the first one is only 1. That's the only time we exclude it. Okay, this is all for covalent compounds, which are 2 nonmetals. Okay, and this time it doesn't have to be the lowest ratio. It's just exactly what's written, right? That's what it's going to be. It's not a ratio. Okay, so make sure you have all of these till 10 written down in your cheat sheets. Yes.
Are the prefixes only for the covalent compounds?
Yes. If you see prefixes, you automatically know that it's a covalent compound. Ionic compounds will never have prefixes on them. Okay, only covalent compounds. So if you have a metal, you're never going to see a prefix with it. Okay, so the prefixes is only for covalent compounds, which are 2 non-metals. And this is just distinguishing between them. Right, aqueous solutions. Right, keep in mind, we talked about electrolyte. Now what happens is when you put a ionic compound in water, it dissociates into its respective ions, and therefore it can conduct electricity. And that is what we call an electrolyte, something that can conduct electricity. Right, so water by itself does not conduct electricity, but it readily dissolves a lot of ionic compounds and therefore makes it able to conduct electricity. Right, and then the last one that we had was our acids, right, for the naming. You have all these different acids that you would need to know. So if you want to write them down in your cheat sheet, that's perfectly fine in terms of the naming, but these are the acids that you will need to know. Okay, any questions? Am I going too fast? We good? Right? I hope we can finish. I've still got a few to go. Right, chapter 6, we started talking about chemical reactions. Right, by now we know how a chemical reaction looks. Everything on the left side is a reactant, the right side is a product. Balancing, we're very comfortable with that by now, right? So practice that if you need to. Please make sure you can balance a chemical reaction very, very fast. There are some tricks in order to balancing things. Right? In this case, we did a half. So a lot of combustion reactions, you might have to use this trick where you use half and then multiply everything by 2. Whereas usually you just look at the number of each element and then figure it out. If you get stuck, you're not able to balance it out, it's a good idea to put the first element as 2 and then try balancing it out again. If you can't, put a 3 and try balancing out again. Guess one of them, it might make it easier for your balancing. Okay, then we know our phases. We have our 4 different types of reactions. Make sure you can identify which one is which. Decomposition, synthesis or combination, single displacement and double displacement. Then we have reactions with metal and non-metal will give you an ionic compound. Right, we went over some examples of that. Another type of reaction, which we did also earlier, was a combustion reaction. Anything reacting with oxygen. We did these same reactions in our redox chapter that we just did. Okay, then you have your aqueous solutions, ionic compounds, solubility. Right, so you will need your solubility sheet. Right, so your solubility table, this will be provided to you, right, for you to figure out if something is soluble or not. Make sure you know how to read it. Right, based on the metal and the non-metal, you should be able to predict if something is soluble or not. If it's not soluble, it will come out as a precipitate. Right, if everything is soluble, you have a no reaction. Went over this in the lab. We did quite a few experiments to test the solubility of specific products. Okay, so this is the precipitation reaction. You'll be given the reactants. You have to swap your anions and then write down what the products are going to be and then figure out if the products are soluble or insoluble. Now for your precipitation reactions, your net ionic equation is usually going to be only considering the precipitate itself, right? So that's what matters. The net ionic equation doesn't have the dissolved particles. It only has what precipitates out. Okay, reactions in aqueous solutions, neutralization reaction. We have a whole chapter on this, which we just went over, which is an acid plus a base gives you water and salt. Okay, any questions on chapter 6? Chapter 7. Right, now we started talking about moles. We went into the calculation, the stoichiometry now. Right, so definition of a mole, and you guys should be very comfortable to convert from a mole to mass, to mole, mole to mass, and all of that stuff. Right, so this should be very easy for you guys now, or you should practice this if it's not. And then we know 1 mole is also 6.02 times 10 to the 23 particles. So if you have to convert between particles to moles, you need this number, which we call Avogadro's number. Right, Avogadro's constant. Right, and this is the first part of our mind map that we drew. Then we went over a balanced chemical reaction. Using the mole maps, you can figure out from one of the reactants or one of the products, you can figure out everything else in your balanced chemical reaction. Right? And then here you have an example of grams to grams calculation, which will require 3 steps. One thing I want to emphasize, and I saw this exam as well, first thing always what you gotta do is just calculate the number of moles. First step in all stoichiometric problems is calculate the number of moles. If you're not given the number of moles. If you have grams, you have to find moles. If you have particles, you have to find moles. If you're given a volume and concentration, you have to find moles. If you're given gas constants and all that kind of stuff, you have to find moles. Okay? Idea is the first step is always finding the number of moles. Then the second step is the same, and then depending on what your product is, the third step can vary. It's always the same 3 steps for stoichiometry. Okay. Then we went over the limiting reactants. Right? Not everything is going to react. Sometimes you will run out of some of your reactants, so it's not going to completely be used up. So in order to find that out, you have to do your calculations to find the limiting reactant. Anything that's not limiting is the one that is in excess. The one that will finish first is going to be your limiting reactant. The way we calculate that is we calculate the amount of products that each of them will make, and whichever one is the lowest, that reactant was our limiting reactant. And the limiting reactant is the one that will be used for all of our calculations. Right, we have the ICE method, which tells you at the end how many of a specific product you have. So you have your initial amounts, which you have your reactants, products are 0. You have your change. And then you add the initial and change to get you your final. And your limiting reactant will always be 0. Your reactants are always negative in the change, and the products are positive. Right, and the last thing that we had for this chapter was using your theoretical yield, which is using your limiting reactant, to calculate your percentage yield. Percentage yield, make sure you have that equation in your cheat sheet. It's the actual yield, which will be given to you, divided by theoretical yield, which you will calculate, multiplied by 100%. And it will not go above 100%. Yield will always be below 100%. Okay. Any questions? 7's good. Now, chapter 8 was a short chapter where we just talked about heat. Now, the main thing in this chapter that you would need to know is Q equals ms delta T.
You just do practice.
Right, your equation.
She does a great
Q
job.
equals ms delta T or Q equals mc delta T, whatever way you want to call it.
She does a great job.
Right, make sure you know how to calculate the amount of heat from your mass, your specific heat, and your temperature. And it's not always going to be Q that you have to calculate. You can calculate M, you can calculate S, you can calculate delta T, and you should know how to do the algebra to calculate anything else. Then if you have your calorimeter, right, in order to find S, right, you have this whole equation that just combines everything in one. Or you can do what we did in the lab, where you calculate the heat, then you go ahead and divide it by the M delta T. Okay, but that equation will be a lot easier if you just want to quickly do the calculations. Okay, so just have that equation written down. Now this is also something we went over a bit earlier, right? When it comes to a reaction, right? If you have a negative delta H of a reaction, that is considered exothermic, right? That is the amount of energy that is going to be generated. If it's positive, it will be consumed, right? But every reaction has a heat associated with it, positive or negative. And based on that, you should be able to calculate, do your stoichiometric calculations as well. Okay, 8 was a pretty short chapter.
I thought that was chapter 7.
Chapter 9. We're almost at that.
Isn't that chapter 7?
9, 10, 11. Chapter 9, covalent bonds. Right, we know what a covalent bond is. We know that everything has to satisfy the octet rule. Right, we identified the different types of electrons that are present around every single atom. Right, be it a bond or be it a lone pair. We know how to draw the Lewis structures. Right, make sure you practice that. Write down the steps if you need to. Right, in order to draw your Lewis structures. These are your steps, 4 steps. Right, add the valence electrons, put the frame, fill the octet of the outer atoms first. Emphasize, please make sure you do step 3 before step 4. I saw a lot of you guys making double bonds, which are not even needed. Okay, so don't rush to make double bonds. So sometimes octet first, make double bonds if you need to.
I don't need a picture of it.
Okay, now the equation for formal charge. Right, formal charge is the charge on each element. It is similar to what we now know as oxidation state. Okay, the equation for formal charge is the valence electrons in the neutral atom minus the covalent bonds minus the number of unshared electrons. Okay, make sure you have that equation written down. Right, these are just Sir Lewis structures. Resonance. Resonance means sometimes you have more than one possible structure. Right, if you have multiple atoms that are the same connection to the same central atom, and one of them has a double bond, it can be either one of them. Right, so this is what we call a resonance structure. It will interchange between the two possible structures. So in this case, 4 different structures, or PO4. Okay, so all of these have multiple resonance structures. But now for this chapter, the emphasis other than that would be our electron geometry. Please have this on your cheat sheet. This whole table should be there with the number of electrons, your electron geometry, your molecular geometry, and everything else. Okay, this is going to be crucial for this chapter. Anything to do with molecular shape and molecular geometry, this is the only table you're going to need. Then we talked about polar bonds, right? Which is you have an unequal sharing of electrons. And in this case, what you need to know is the numbers 0.5 and 2. If it's less than 0.5, it is covalent. If it is anywhere from 0.5 to 2, 0.5 included, it is polar. Okay, it's a polar covalent. And anything higher than 2 is going to be an ionic compound. So 2 and 0.5 are included in polar. Right? Polar includes the 0.5 all the way up to 2. Below 0.5 is covalent, and above 2 is ionic. Okay? That is for the specific bond. Now for the molecule, it depends on the entire molecule and its geometry to figure out if it has a net dipole or not. So keep that in mind. Each of these are like a pulley, right? The electrons are trying to be pulled. So depending on if there's an angle or not, you will end up with a net dipole. Now remember the rules I gave you guys, or the tips, tricks to remember that. If you have a lone pair, and the bond is polar, then likely the molecule will also be polar. If you have no lone pairs and all the atoms are the same, then it's always going to be non-polar. But if you have no lone pairs and you have all different atoms, and any one of them is polar, then the entire molecule will be. Okay? Any questions? Now, chapter 10, we're talking about solid, liquids, and gases. Right? We talked about the different types of solids that we have, solids and liquids, ionic, metallic, stuff like that. Right? And then we talked about the 3 different types of intermolecular forces. You have dipole, you have hydrogen bonds, and then you have dispersion forces, or dispersion forces. Right, dipole is when you have a polar molecule, right? It will result in a higher melting point and a higher boiling point. And then you have hydrogen bonding, which is an extreme case of dipole, and it only exists with 3 different atoms. NOF. These are the 3. If any of these 3 are connected to hydrogen, that will cause what we call a hydrogen bond. Only these 3. Anything else, it's not a hydrogen bond. Okay, these 3 connected to hydrogen. So these are 3 examples. Right, sorry, not this one. Right, you have water over there, which is hydrogen bond. Examples are not given. The idea is you either have H2O, NH3, or HF. Right, those are 3 that we have hydrogen bonds. But keep in mind, it doesn't have to be two hydrogens, it could only be one hydrogen, and it could be a completely different organic molecule. Organic molecules with OH, right? The alcohols that we call them, they all have hydrogen bonding. Okay? Okay, London dispersion is the weakest of all the forces, right? It's an instantaneous dipole, right? For a fraction of a second, it really is a very, very weak type of bond, and it only comes into play when you have a really large molecule. Now, in terms of strength and order, hydrogen bonding is the strongest, and London dispersion is the weakest of all of the types of bonds. Then we talked about gases, right? And we got into our gas laws. The two gas laws you would need to know are going to be your combined gas law, right? P1 V1 over T1 equals P2 V2 over T2. Please make sure your temperature is in Kelvin. In this case, pressure and volume have to be consistent. They don't have to be specific units. They just have to be the same. Okay, this is your combined gas law. And then you have your ideal gas law, PV equals nRT. In this case, everything has to be in a specific unit. Pressure has to be in ATM. Volume has to be in liters. N is number of moles. R is going to be this value that we have over here, 0.0821 liter atmosphere per mole Kelvin, and temperature has to be in Kelvin. Okay, and then you just have to rearrange the equation to solve what you need to. Yes?
If we're given R and we need to convert it, like we have it in a different form of pressure, is the conversions going to be given?
For R?
Mm-hmm.
Or for the conversions for pressure? You'll be given the conversion for pressure. For example, if you're given a pressure in torr, you will also be told how many torr in one atmosphere. But the R value that we are using is going to be this one. I'm not going to give you a different R value.
So we wouldn't have to change the R to torr?
No.
Okay.
The R always stays as liter atmosphere per mole Kelvin, and you change the pressure to torr, and you change the volume to liters before plugging it into the equation. The R value doesn't change.
Yeah.
For now, for our class.
Okay.
Right, there are different R values that you use when you're dealing with other cases. Okay? What? N? N is mole. N is mole. Mole, temperature, pressure. Then you have partial pressure, right? You can use the equation for different components in the entire mixture. Right, and the total part of partial pressure, if you add all of them, it will give you the total pressure of your gas. Right, and the last part in this chapter was your gas stoichiometry. Right, we're just adding that since it's another way of calculating the number of moles. Now we can use that in our stoichiometric equations. Okay, so now we have grams, particles, gas, energy, all of these different parts in our mind map. Okay, so make sure you guys go ahead and practice an equation or a question with this type of calculation. And our last chapter for today is chapter 11, which we talked about solutions. Right, we're talking about concentration now. Right, we have mass percent, volume percent. I said we're not going to be dealing with these, neither are we going to be dealing with ppm. What we are going to be dealing with a lot is molarity. This is something we have been using a lot in the lab nowadays, right, after we went over this concept. Molarity equals moles divided by volume. So make sure you know how to calculate anything that is given to you. Right, this is in terms of preparing a solution. So you should be able to tell me how much of a specific volume you have to use. In this case, if we are diluting something, as soon as you see the word dilution, you should remember this equation: M1 V1 equals M2 V2. That is for dilution. Oh, it's there. Okay. Then we have our equations, right? And now we're adding this molarity and volume once again to our stoichiometry. And the whole purpose of adding molarity and understanding that was to add it to our stoichiometric equations, because this is the most commonly used way in the lab that people will calculate number of moles. You have a volume of a liquid and you have to know the concentrations, right? And then that is going to be used in your stoichiometric calculations. So go ahead and practice that, right? And have your entire mind mole map. That will help you. Gravimetric? Sure. It's just another type of calculation, right? I don't specify this as a different type of stuff. It's just another stoichiometric question which goes from grams to concentration, right? It's just another path that you can take on the mole map. Alright, hey guys, good luck, right? And have a great semester. I'll see you guys next week. Let me know if you have any questions. Please send me an email. I'm always available to help. If you guys need to ask any questions. Okay, guys? I'll see you on Thursday.
Is that your cheat? You said yeah?
No.
Oh, no, okay.
Oh my god.